Hello everyone. Welcome to webinar number 7 for year 12. Today's topic is center of mass. And center of mass is something you're kind of familiar, you kind of know what this is talking about. So if you take like a ruler, and the center of mass of a ruler is somewhere in the center, right? So you can tell because you can balance it on the finger, right? If you attach something to the ruler at one end, then obviously the center of mass moves because now it is the center of mass of the ruler plus that black thingy I'm holding, whatever that is. So now it's the center of mass of two objects, and the center of mass of the two objects is somewhere here around this 5 centimeter mark on the ruler. If you take a object with uneven distribution of mass, you can balance it somewhere here, and that's roughly where the center of mass is. So center of mass is just above my finger. Yeah, so I kind of knew intuitively you understand what center of mass is. So let's introduce a slightly more formal definition of center of mass. I'm going to share my screen, and if you have several objects, and for example, if this is the x-axis, and this is 0 on the x-axis, and there are three objects, let's say M1 at a point with coordinate x1, M2 at a point with coordinate x2, and a point M3 with coordinate x3. So we're doing it only one-dimensional case. So we're just looking at three masses in 1D, right? So there can only be one distance, which is the distance between the points. So the coordinate of the center of mass, x of the center of mass, is m1 x1 plus m2 x2 plus m3 x3 divided by m1 plus m2 plus m3. And that's about it. It's called the weighted average actually. And yes. Now if you have 3 points in in a 2D case, so in 1D, in 2D. In 2D, well, you have, let's say you have 3 points, like this, M1, M2, M3. But every point has an X coordinate and the Y coordinate. So you would find the X1, X2, and X3. And on the other hand, this is Y1, this is Y2, and this is, sorry, Y2, and this is Y3. So you would see very similarly, so X center of mass is M1 X1 plus M2 X2 plus M3 X3 divided by M1 plus M2 plus M3. And Y center of mass is M1 Y1 plus M2 Y2 plus M3 Y3 divided by M1 plus M2 plus M3. Okay, these two formulas can be combined and to find the position vector, so the R center of mass, so vector R center of mass is M1 R1 plus M2 R2 plus M3 R3 divided by M1 plus M2 plus M3. Any questions, please ask in the chat. Don't be shy. I hope you understand what M1, M2, M3 mean. So R1, R2. R1 is the vector drawn from the origin to M1. That's the position vector R1. This is vector R2, and this is vector R3. And this rate RCCM, so let's say the center of mass is somewhere here. So the center of mass and the radius vector drawn to the center of mass is this. So this is RCM. Okay. And we're going to use that for problem 1. Four 4-point masses, M1, M2, M3, and M4, are located at the 4 points, 4 respective points. We don't need to draw them because this is in a three-dimensional case. So the position vector of the center of mass, we already know it's M1 R1 plus M2 R2, M3 R3, and plus M4 R4 divided by M1 plus M2 plus M3 plus M4. And that is, so M1 is 6. Multiply the position of R1. So R1 is minus 3, 2, 1 plus 4 multiplied by 1 minus 1, 4 plus M3, which is 5 multiplied by 4, 0, 0 and plus 4, so that's 2 multiplied by 8 minus 4, 2 all over 6 plus 4 plus 5 plus 2, which is, well, 10, 17, so that's 17, and that's a vector, so it's minus 18 plus 4 plus 20 plus 16, 12 minus 4 plus 0 minus 8, 6 plus 16 plus 0 plus 4, and that's 1/17. And the vector is, well, that's 2, 6, 22, 0, and 20 plus 6, 26. So that's 22/17, 0, and 26/17. So the center of mass, so the answer, the center of mass is at point 22/17, 0, 26/17, of course. We're talking about the center of mass. We're talking about centers of mass, and yes, this is webinar 7. Okay, so yes, there you have the Miro board. You can use it. You can trace what I'm doing. So basically, to find the center of mass, you need to know the masses and where they are, the positions of the points. Okay, so problem 2. How far is the barycenter, the center of mass of the Sun-Jupiter system, from the Sun? Okay, so we have the Sun, we have Jupiter, not to scale. The distance is certainly not to scale. And let's draw an x-axis going through Jupiter. Let's put this. How far is it from the center of the Sun? So we're interesting from the center of the Sun. So we might as well just say this is 0. This is 0 kilometers. Right, Jupiter. How far is Jupiter from the Earth? Well, let's say Jupiter The sun is position x1, Jupiter is position x2, and we'll need to look that up. Mass of the sun is m1, and mass of Jupiter is m2. Okay, so let's look those up. Mass of sun. I'm pretty sure it's 2 times 10 to the 30. Good. So that's 2 times 10 to the 30 kilograms. Mass of Jupiter. Jupiter. And that is 1.9 times 10 to the 27. 1.9 times 10 to the 27 kilograms. So it's 1,000 times less. Oh, I didn't know that. Okay, that's interesting. Right, and then distance. Distance, a sun to Jupiter. 777, 777. Okay. So if sun is at 0, this is a 777 million kilometers. So that's times 10 to the 6 kilometers. All right, we can do it in kilometers. And let's write this position of a center of mass. So the center of mass would be somewhere here. Center of mass, xcm. So x center of mass is going to be m1 x1 plus m2 x2 divided by m1 plus m2, which is m1 is 2 times 10 to the 30 times 0, so that's 0 plus 777 times 10 to the 6 times 1.9 times 10 to the 27 all over m1 plus m2. Well, m1 plus m2 is pretty much 2 times 10 to the 30, right? Because 2 times 10 to the 30 plus 2 times 10 to the 27 is 2.002 times 10 to the 30, if I'm not mistaken. 1.9 times 10 to the 27 plus 2 times 10 to the 30. Yeah, okay. I'm not mistaken. And then we can just calculate the distance. So 777 times 1.9 times 10 to the 33 to the 33 divided by 2.002. Oh, no. Divided by 2.00. That's 10 to the 30. Okay, so it's 0.74 times 10 to the 6 kilometers. Okay, 0.74. So that's much closer. That's much closer to the sun. Let's look at the radius of the sun. Radius of the sun is 695. 695. So 0.7 radius of the sun. The sun is 0.7 times 10 to the 6 kilometers. So the center of mass of the sun and Jupiter is actually just outside the sun. And that kind of makes sense because it's not like Jupiter goes around the center of the sun. No, the sun and Jupiter go around a common center of mass. If you think about it, like let's say that this is the sun and this is Jupiter, they go around the center of mass like this. So they both rotate around one another. I can show you uh, bed orbits. And let's see if we can model and path routing. Oh, start. Okay. Okay. Um. Okay. So it's difficult to see, but the sun, the star, is also moving. It's just not very obvious, but yeah, I thought it was much more dramatic, but it isn't for some reason. Right, but anyways, the star does move. Oh, you can use the grid. No, you can't see that. Oh, what's going on? Okay, reset. Still no? Okay, apologies. I was sure it was this model allowed you to see the wobble of the sun. Sometimes you can detect the presence of planets like that, right? You need to understand prior knowledge to understand this. Well, I think there we have some sort of proof of the form. I don't remember if we have the proof of the formula in the assignment, but no, you just need the formula for now, and hopefully that formula makes sense. So yes, so the center of mass of the Sun Jupiter is just outside the Sun. Effectively, the Sun rolls around that point, so the Sun moves quite significantly, right, as Jupiter goes around it. Moving on. Uh, three. Okay, this is a weird sounding question. A sealed transparent cylinder of mass m and length l lies horizontally on a perfectly smooth ice with no friction. So we have a container which is sealed, so closed at all ends, and it is on a frictionless surface. There's a question, how do we combine the pull from other planets along Jupiter to figure out the motion of the sun? That's an incredibly difficult task. And it's sometimes known as the three-body problem, basically, when you have more than two objects moving around one another, the mechanics becomes incredibly difficult and incredibly unpredictable. So yeah, you use complicated models to predict the motion. But it is possible. It is possible. But even a slight mistake in the calculation of the position will lead you to different paths. So it's like the butterfly effect. A small change creates a large change afterwards. But anyway, so we have a fly. Let's draw my best fly ever. So a fly of mass m, and the container is mass m. And now they're both stationary. Okay, they're both stationary. And now the fly decides to fly from one end to the other. Okay, now they say find the displacement of the cylinder relative to the ice. So the cylinder should move. Why would it move? Can anyone help me with that? Why would the cylinder move in the first place? Like, it's just a fly going from one end to another. Center of mass changes. Well, yes, the center of mass changes relative to center of mass changes relative uh to the to the container, certainly. Angular momentum. I'm not sure what I'm not sure how what you mean by that. When it's pushing off the ground. Interesting. So are you suggesting that it's jumping rather than flying off? Because once it's in the air, it's not no longer pushing against the can. When it pushes off the ground. Well, if it was crawling, if it was crawling from one to another, that would make sense. There's friction, right? They push against the jar, so the fly pushes the jar. The jar pushes the fly back forwards, right? In order for the fly to accelerate forward, the jar has to push the fly forwards, and the fly must push the jar backwards. That is very, very true. Um, and the same idea, if you're jumping inside the can, if you jump, you push against the jar, so the jar moves backwards, just like jumping in a boat, right? If you're standing in a boat and you jump forward, the boat would go backwards. Very good. The fly beyond the motor before to throw. Okay. Well, the fly does have a built-in motor. It's his muscles. Yes, it has chemical energy. So it's actually pushing the air. In order to fly forwards, the fly must push the air backwards. And that air, when it hits the back wall, it pushes the can back. So, in a way, that is, you're correct. It does have a motor to thrust. Yes, so the fly pushes the air, and the air hits against the back wall, and that pushes the cylinder backwards. Right. But there's a very important statement that I want to make. I don't want to prove it, at least today. So important, important statement. Let's put it that way. The center of mass. Oh, there is air in the cylinder because otherwise the fly wouldn't be able to fly if there was no air. Important statement. The center of mass of a system uh, cannot be moved by internal forces. Okay. Internal forces. So there are internal forces and there are external forces. And the external force would be someone picking up the can and throwing it, right? Or wind pushing the can forwards, or anything else. Or friction, right? The friction, if there's friction, the friction can cause the can to move or slow down. Friction can do both things. But the fly pushing against the air, that's an internal force. And the air pushing the can is an internal force. And therefore, the center of mass must remain where it is. Center of mass, center of mass will not move. Okay, so let's find that center of mass. And the center of mass of the can is obviously here. That's the can. And the center of mass of the fly is here, where the fly is. All right. So um, if we draw the x-axis, let's put the fly at position 0, and the center of the can is going to be L over 2. All right. Now, once the fly has moved, the whole cylinder has shifted. Let's say this is the new position of the cylinder, of the container. And let's let that displacement be x. Is that a good idea? No, that's not a good idea. Let's make this d. So the fly hasn't moved a distance equal to the length of the cylinder. The fly has moved a distance L minus d, because the fly has flown L, but the cylinder has moved d to the left. Right. So the fly this is the new position of the fly here. Right. So that wasn't a very good drawing because it doesn't include the shift in position of the cylinder itself. Okay. And then so that's the new position. That's the new position of the fly. And right. So center of mass before fly moves. And the center of mass before fly moves, x center of mass is m1 x1 m1 plus m2 x2 divided by m1 plus m2. So that is the mass of the fly, which is m, then the position of the fly is 0, plus the mass of the cylinder, which is capital M, and then the center of mass of the cylinder, which is L over 2, divided by m1 plus m plus m, which is ml over 2, open bracket, m plus m. Lovely. Center of mass after the fly moves. So the cylinder has shifted by d to the left. So the new center, the point M has shifted by d to the left. So the new position of the center of mass is mass of the fly multiplied by the position of the fly, which is L minus d, plus mass of the cylinder multiplied by x, which is L over 2 minus d, because that's the new position of the center of mass of the cylinder. Okay. And that's divided by m plus m. Now, we know that the center of mass has not moved. So the old center of mass must equal to the new center of mass. So we just make them equal to each other. So ml over 2m plus m equals, let's open the brackets. So ml minus md plus ml over 2 minus md divided by m plus m. So m plus m cancels, and we get ml over 2 equals ml minus md plus ml over 2 minus md. So ml over 2 cancels, and we get small ml is equal to md plus md. So d is equal to m over m plus m L. So that's the distance moved um by this the cylinder. Okay. So if you had some numbers, um, example, example. If you had the mass of the fly is 2 grams, the mass of the cylinder is 6 grams, and the length of the can is 60 centimeters. So we would see that as the fly moves from one end of the can to the other, so 60 centimeters. Well, it doesn't actually move 60, it only moves 60 centimeters relative to the can, but not to the ground. So this D would be 2 divided by 8 times 60 equals 15 centimeters. So the can would move 15 centimeters. Akash, that is spot on. That's exactly what it means. If you take a bomb, put it in space, and you pull the trigger, the pieces fly away in different directions, but the center of mass of the bomb remains where it is. I'm very pleased you asked that question. Yes, that's exactly what it means. So if you have a shell, let's say a bomb that breaks into 4 pieces, M1, M2, M3, and M4, and it flies away, all the pieces fly in different directions. With different speeds. But as they fly away, if you calculate the center of mass, yes, it does exactly link to that fact that uh, the total momentum is 0. Absolutely. And that's what the same thing we have here. The total momentum of the fly plus the can is 0 because they were initially stationary. And another important, well, not another important one, but there was a project, there was an idea, perhaps 80 years ago. Somebody proposed, what if we build a rocket which looks like this? Um, so this is a chamber which looks like it's a hemisphere or more like a half ring sort of, and the astronauts would sit inside. Because it was a long time ago, they kind of thought that the astronauts would be sitting on wooden chairs for some reason, because that was like beginning of the century, so beginning of the previous century. So they would sit and drink tea, and right, and there would be like a I don't know what they would do. Listen to music. So there would be. If you look at very old pictures of future space flight, they really thought it would be like this: people sitting in leather chairs, drinking tea, and there would be music playing in the background. Right. So inside the wall, so it's a double wall, and there's a pump here. So there's a pump, and it pushes water or other liquid around the this pipe at very high speed. And because the upper surface is curved, there will be a centrifugal force. So there's a centrifugal force on the water as it goes around in a circle, right? Just like if you go around a tight corner, you feel that ooh, centrifugal force going sideways, and that would push against the upper surface, right? The upper surface of the rocket, and this would provide the thrust. So that would push the rocket upwards. So what's the problem with this method? Why can't we build rockets like that? Why can't we make them fly? Think about internal and external forces. If you want the rocket to fly upwards, that means you're changing the center. There's changing the position of the center of mass. But all you have is internal forces. So internal forces don't. It is well. It is related to Newton's third law. So internal force launch something. Well, that's not the point. Like I mean, let's suppose the walls were strong enough. It would still wouldn't work because internal forces cannot lift cannot change the position of center of mass, cannot move the center of mass. So why in this case this wouldn't work? Well, because yes, we are considering this force on the top, but we're not considering the force when the water changes direction here. There would be a very large force going downwards, down and left, and there would be a very there will be a strong centrifugal force going down and right, and these two forces would compensate that upwards force, and that's it. That's why it wouldn't work. Um, okay. And next one, a uniform circular disk of radius r. Okay. Wow, we've spent 40 minutes on the first three questions, and I haven't gotten to the hard ones yet. Okay, uniform circular disk of radius r has a circular hole of radius r. The center of a hole is a radius of r3, r over 3, so half, half. So there's a hole here, and the radius r, and the distance is r over 3. Find the position of the center of mass. So from the picture, you could guess that the center of mass would be somewhere here, would be on the right-hand side. Center of mass is here. So we draw the x-axis. Now, and let's place the center of this at point 0. If a person was to punch the wall of the container hard enough, which is a rocket, would the rocket go up until the person's arm moves back down? Well, if you think about it, if you're standing on the floor, so you hit the ceiling, and the ceiling is pushing your hand down, and your hand is pushing your body, and your body is pushing the floor. So as the same time as you're pushing the ceiling up, your body is pushing the floor down with an increased force. So yeah, that wouldn't work. Now, if you were to jump into the air and then kick the ceiling, yes, momentarily the ceiling would move up, but your body would move down, and the center of mass would stay where it is. If that makes sense. Microgravity environment. If you're talking about like a space station, microgravity, uh, very similar. So would you fly until you go back down? Would you fly until you go back down from jumping? Well, yeah, the rocket would can lift. I mean, imagine you so getting internal forces to lift something is like trying to lift yourself pulling your hair up. Yes, like Munchausen tried to do. So he pulled himself, he lifted himself pulling on his hair, and he lift, which is obviously impossible. Or if you sit on a chair and you try to hold the chair and try to lift yourself with the chair, also impossible. You can jump. You can create a jerky movement and get yourself to jump, but that wouldn't get you to fly. How can the hamsters roll in the ball then? Because there's an external force, and that external force is friction. There's a friction against the floor, and that friction pushes the ball forwards. That's a very good question. How can hamsters roll in a ball? I'll just highlight this one. On the ball, because the hamster pushes on the ball rolls, the ball rolls forward, so it wants to slip against the floor, but the floor is preventing that, so there's a friction going forwards, friction, and that friction pushes the ball forwards. That's a very good question. Thank you for that. And just like the car, like how does a car move itself forwards? Right? Think about it. The engine, well, no, that's an internal force. The engine doesn't push the car forward. Friction does. Yes, the friction against the ground. So the wheel tries to spin, but there's friction that prevents the wheels from spinning. That cause the car to go forwards. I like the way people are thinking today. Lovely. Right. So this is a lovely question. So we take a circular disc and we cut a hole in it, and now we need to find the center of mass. This is an incredibly similar question to the one in the assignment. A little too similar. I kind of regretted this one, but I didn't have any other good question to replace it with. But anyways, so what you're going to do is you're going to cut another hole. Let's cut another hole. Symmetrical to the first one, and we're going to cut it here. So now we have two objects. Now we have two pieces, a disc with two holes in it, and a small piece, right? This is the piece which we cut out from here. Does that make sense? And now we need to find the center of mass. So the mass of this piece, M1 and M2. Well, the mass of this piece is pi r squared minus 2 multiplied by pi r squared. So we've cut out two holes, and that's the area. And area multiplied by sigma is the mass. So mass is the area multiplied by sigma, which is called the surface density. Surface density. And mass of the second piece is simply pi r squared. Sigma, of course. Pi r squared sigma. Now the position, x1, of the first piece is 0, because the center of mass is here. The position of the second piece is r over 3. And that's all. That's all we need. Do you understand this one? So how well do you understand on a scale of 0 to 10? Do you understand what I just did? I found the center of mass of this piece, 0, and the mass is equal to the area multiplied by sigma. So the mass of this piece is this. Pi r squared is the area of the big circle minus 2 areas of the small one. And the small circle has area pi r squared. And the position of that mass. Okay, so there's a lots of 5s and 6s. Okay, that's fine. Once again, I have a disk with a hole in it. I say it's the same as having a disk with 2 holes and a small disk that exactly covers the second hole. Agreed? Now we need to find the mass of the first piece. The mass of the first piece is the area multiplied by sigma. And the area is pi r squared, that's the big circle, minus the 2 areas pi r squared minus pi r squared, and multiplied by sigma. Mass of the second piece is just pi r squared sigma. All right, are you happy with that? Is that better now? So if your score has increased, can you type the new updated score, please? If your understanding has increased. Okay. Now we now need the position. We need the mass and the position of each piece. And we need the mass and the position of each piece. So the position of the first mass of the disk with 2 holes in it is 0 because it's at the center. We purposefully placed it in the 0 at the center of the radius because the shape is now symmetrical. Now we know where the center of mass is. The center of mass of the small disk is at position r over 3. So we say x2 is r over 3. x1 is 0. Right. So now I just need to calculate the center of mass. So x center of mass is m1 x1 plus m2 x2 divided by m1 plus m2. And all I need is to calculate. And m1 is pi r squared minus 2 pi r squared multiplied by sigma multiplied by x1, which is 0, plus m2, which is pi r squared sigma times r over 3 divided by pi r squared minus 2 pi r squared plus pi r squared sigma, x center of mass, and sigma. Well, pi, of course, cancels as well. So we have, oh, that's 0. Okay, 0 plus r squared r over 3 over r squared minus r squared, which is r squared r over 3 r squared minus r squared. Lovely. What is the hole is too big and there's an intersection between the imaginary hole and the actual hole? Well, not in this case. If that would be the case, then yes, it would be a more complicated area. Um, I meant to say R over 3. Yeah. Um, and in the assignment, you will have R over 2. Okay, getting to the difficult part. Let's put it that way. Right. Using Riemann sums by cutting into vertical strips, find the center of mass of a uniform quarter circular plate of radius 2. So we have a quarter circle. So quarter circle. Okay, quarter circle, and let's draw the axes. Okay, and it's 2 meters, 2 and 2, x, y. Now we're using Riemann sums. So is there a general? Oh, sorry. Is there a general method to find the center mass of irregular objects? Usually, yeah. To find the center mass of an irregular object, you break it down into a known objects. Yeah. So, for example, if you have an object like this, so you break it down into rectangles. Find the center of mass of each rectangle. M1, M2, M3, and then find the center of mass of the 3. Yes. Oh, if the circles were overlapping, then you would calculate that area, I guess, and subtract and then find that area, and then you do the area of this first circle plus area of the second circle minus the overlapping areas. You could use trigonometry to do that. You wouldn't need to. You would need to use trigonometry to. Anyways, let's get to this one. So we have I need to find the center of mass. So the center of mass obviously will be somewhere here, but sort of the center of mass is here. Because it's symmetrical, if you just find the x, that means you automatically find the y, right? Because if x is, I don't know, 0.7, then y is also 0.7. I hope that makes sense, right? It has to be like that. Now, so the center of mass is somewhere here. So what I'm going to do is I'm going to cut this disk into vertical strips. And I say that if this strip is narrow enough, if this width, let's call it delta x, is narrow enough, I can assume that is a rectangle. It looks like a rectangle. Okay, I'm cheating a bit here, but hopefully you're happy with that, right? So I'm saying, well, the area of that rectangle, or so looking at that rectangle, this is delta x. That's the width of that rectangle, and the height of that rectangle, well, there's just y. There's just y. So the area is y delta x. So the mass if we know the surface density is area multiplied by sigma, which is y delta x sigma. Right? Nice. The center of mass is of course x. So x is this position. X is how far the rectangle is from the center. Position is x. Right. So for all the rectangles, the center of mass of all the rectangles is m1 x1 plus m2 x2 plus etc. And let's say it's n rectangles plus m n x n, right? Divided by m1 plus m2 plus etc. plus mn. So x center of mass is equal to the sum of mi xi, the sum of these rectangles, divided by the sum of the masses. But the sum of the masses is just the mass of the quarter circle. So that's pi r squared over 4, because it's a quarter circle, multiplied by sigma. So that one's easy. And then here I'm getting something interesting. So it's the sum. Mass, we already know that the mass is y delta x sigma, multiplied by x. So that is the sum of x sigma x y delta x divided by pi r squared over 4 times sigma. Okay. Now, sum of x's. Well, sorry, I've missed a step here. Imagine that this is an ith rectangle. This is the ith rectangle, because I've numbered them, right, from 1 to n. So this is a rectangle number I. So 1, 2, so 1, 2, and this is number I. And the distance is xi. The height is yi. Delta x. Delta x, we can say, assume delta x is fixed. And this is y ai xi, and this is yi xi xi yi. Lovely. Now, let's remember this is a circle, right? This is a circle. The equation of a circle is x squared plus y squared is r squared, small r squared. So y squared is r squared minus x squared. So y is plus or minus square root of r squared minus x squared. I don't need the minus because I see that y is positive. So y is square root of r squared minus x squared. So I plug that into here. So this is going to be sum of sigma xi multiplied by square root of r squared minus xi squared delta x I r squared over 4 over sigma. And the sum is from 1 to n. Now, this is called the Riemann sum. Riemann sum. So what I do now is I make delta x smaller. that means that n is increasing, the number of strips is increasing. So let delta x become very, very small. So n becomes infinity. So we're looking for the limit as delta x tends to 0 of this expression. And if you think about it, like the adding up, so this actually is equal to the integral of sigma x square root of r squared minus x squared dx. So delta x becomes dx because dx is an infinitely small change. That's how Riemann sums work. And now it's an integral from, of course, x changes from 0 to 2, or 0 to r. 0 to r. And that's how you do it. And then, so x center of mass is the integral of 0 to r sigma x square root of r squared minus x squared dx over pi r squared over 4 sigma. Now, sigma cancels. Of course, it's a constant, so we don't care about that. So it's going to be 4 divided by pi r squared multiplied by the integral of 0 to r x square root of r squared minus x squared. Now, I wouldn't be surprised if you didn't know how to do this integral. So you're allowed to look up integrals. So do try to do them, of course, but if you don't know how to integrate, so integral of x square root a squared minus x squared, not this, square root of x times, yes, and here it is. You can use that result, or let me integrate it. Honestly, we're running out of time, but it's going to be this. Right. So that's equal to multiplied by 4 pi r squared, and this is between limits of 0 and r, and you substitute r. If you substitute r, that's 0. If you substitute 0, that's just 4 divided by pi r squared. R squared multiplied by square root of, so r squared, sorry, r squared over 3. So it's 4 r cubed divided by 3 pi r squared. So it's 4r divided by 3 pi. And that's the position of the center of mass. Okay, so center of mass, here this is 0, 0, x and y, then the x position, so it's 4r. So because r equals 2 meters, x center of mass is 4r, 4 multiplied by 2 divided by 3 pi, which is 8 over 3 pi. So this point has coordinates 8 over 3 pi, 8 over 3 pi. So I hope that wasn't too harsh, but yes, we're getting into hard stuff now. And now the second piece, the same idea. By slicing a uniform half cylinder of radius 2 meters of length. So we have a half cylinder and we're slicing it into vertical strips. So take strip number I, and you can see that this is 2i, 2y. So this is x, and this is y. This is 2y, and the center of mass, the position is xi, and the area, so the mass is sigma multiplied by 2yi multiplied by delta x, and then the x center of mass, and this is 2. X center of mass is the sum of mi xi divided by the sum of mi. Okay, so that is oh, sorry, density. Density times length. Density times length of the cylinder. Apologies, of course. Of course, the length of the cylinder is the cross-sectional area times the length, right? So the volume is A L, so and the mass is density times volume. So mass is density times cross-sectional area times the length. So that's what we use here. How do you find the coordinates of the center of mass of an object that isn't symmetric? Well, different there are different methods, but effectively you break it down into objects uh, of known center of mass. So that's effectively what I'm doing here. I'm breaking down a semicircle into rectangles, well, into blocks. So one block is like this. So we cut out a piece like this, right? And so the volume of that piece is delta x multiplied by 2y multiplied by L. So the mass is density times L times 2y times delta x. And so we substitute that in. So the sum of rho L 2yi xi delta x, and the sum of masses, well, that's just the mass, so it's a cross-sectional area, pi r squared divided by 2, multiplied by the length and multiplied by the density. Density and length cancels. That's good. So it goes 2 divided by pi r squared multiplied by the sum of 2y, and y is equal to square root of r squared minus x squared. Again, the sum of 2xi square root of r squared minus x squared, and divided by, yeah, dx, delta x. And then as the limit as delta x tends to 0 of the sum of 2xi square root of r squared minus xi squared delta x is the integral from 0 to r of 2x square root of r squared minus x squared dx. And we already know that integral, so that is minus 2 r squared minus x squared square root r squared minus x squared over 3 between limits 0 and r. And if we substitute r, that's 0. If you substitute 0, that is minus 2 r cubed over 3. Okay, so we substitute that in. We substitute that into here. So that's 2 over pi r squared. So small r, pi r squared, and multiplied by plus 2r cubed over 3. So it's the same, 4r over 3 pi. So it's the same result, of course. The integral, the sum becomes the integral. So look, this sum symbol is replaced with the integral symbol, and delta x is replaced with dx, and everything else is the same. Because the integral is the sum. The integral is the sum, but the integral is the sum of infinitely many pieces. That makes sense. If you think about it, like if you have a function f of x and you have these strips, and every strip has height y, y1, y2, y3, y4, y5, y6. So the area is, and this is delta x, delta x, delta x. Area is y1 delta x plus y2 delta x plus y3 delta x plus etc., which is the same as the sum of y I delta x. So it's the sum of all y's delta x. But as if you take the limit as delta x tends to 0, yi delta x, it becomes the integral of y dx between limits a and b, a and b. And we already know that this is the area under a curve. Yeah, under the curve. Right? This integral is the sum of infinitely many, infinitely narrow strips, vertical strips. So yeah, that's quite fascinating. There's a lot of maths here. And yes, so we found the center of mass of the cylinder is here. Is 4r over 3 pi, and which is in this case, again, the radius is 2. So x center of mass is equal to 8 over 3 pi meters. Okay. In general, x center of mass is 4r over 3 pi. Okay. Problem 7. A vehicle has track of 2.4 meters and its center of mass is 2.2 above the ground. So let's draw bus tested tilt. Ah, that's an amazing picture. Right, so this is how buses are tested, so that they don't fall over. So we have a track width. So this is 2.4 meters. So this is 2.4 meters. And the center of mass is 2.2 meters above the ground. So the center of mass is 2.2, sorry, 2.2 meters above the ground. So the bus will tilt when the line drawn through the center of mass, the draw is here, like the edge. So the bus topples over when the center of mass goes over the wheel, effectively. Okay, so let's do some measurements. So let's label these. because let's label these orange. Would that work? A, B, and C. So we have B, C, and A. And AC must be a vertical line, vertical, for it to topple over. So this is 2.2 meters. 2.4 meters is the base, so that's 1.2 meters. This is a right angle triangle. And this is the angle of tilt. This is the angle theta. And if this is theta and this is vertical, that means this is 90 minus theta. And if this is 90 minus theta, then this angle is theta as well. And from here, we can see that tangent theta is 1.2 divided by 2.2. And then theta is arctan of 1.2 over 2.2. So 1.2 arctan 1.2 divided by 2.2. So which is 50 degrees. 50 degrees. That's the maximum tilt that you can have on this particular bus. I don't know how realistic these numbers are. I think a normal bus would topple at around 40 degrees. Certainly not 30, but yeah. You can look it up. When would a London double decker bus topple over? Show with the diagram an argument that uniform solid hemisphere placed on a curved side down on a horizontal surface stable equilibrium. Okay, let's skip that one because I really want to do the next one. A uniform half cylinder of mass m and radius r rests on its curved surface. Right, so we have a uniform half cylinder like this, and a mass m and radius r. Now, we put a small mass on the edge. We put a small mass on the edge, and what happens is that this mass tilts because now it has a mass. Mass is here. Okay. Well, first of all, we want to know where the center of mass is. So the center of mass, we already know that the center of mass is 4r over 3 pi distance away. So the same thing here. We draw center of mass, so it's 4r over 3 pi distance away. And this mass, well, that's just r. And imagine that it tilts by an angle theta. So if you draw a line like this, well, this is where it touches it. So I'm gonna just delete that old one. And we know that this is theta. And this is theta. All right, so what we are interested in, because the center of mass must be here. The center of mass must be here because it's resting on a single point. Center of mass. Mass is here. Okay, so let's take that this is 0 on the x-axis. Why not? And we say we need to find where this mass is. And this mass is, so we need to find this distance, x1. And we need to find this distance, x2. Well, x2 is easy. x2 is r multiplied by cos theta, right? Because if you draw a triangle, that's this distance, r cos theta. Now this one, well, we can draw a right angle triangle like this. So this distance is going to be x1 x1 is 4r over 3 pi multiplied by tan theta. And then m1 is just m, and m2 is small m. Ta-da! That's it. That's all we need. Once you figured out the two objects, so you have two objects, the big mass and the small mass. You find the position of the big mass, you find the position of the small mass, and that's it. That's all you need. So the center of mass, so the angle of tilt, and the center of mass is at 0. Center of mass is at 0, so x center of mass is 0, and it's equal to m1 x1 plus m2 x2 divided by m1 plus m2, and that's equal to, sorry, x1 is minus that because it's obviously it's negative, it's to the left. So it's minus 4r over 3 pi tan theta plus multiplied by x1 multiplied by m plus r cos theta multiplied by small m all over m plus m, and that must equal to 0. Therefore, r cos theta m is 4r over 3 pi tan theta m. R cancels. So okay, and cos theta m equals, it's a little bit, oh, um, okay, looks like we have to do a quadratic, really. Cos squared is okay, so 3 pi m cos theta equals 4 m tan theta. Tan theta is sine over cos. Throws 3 pi m cos theta equals 4m sine theta over cos theta. Then we we multiply it by cos theta, so we get 3 pi m cos squared theta equals 4m sine theta. So cos theta is 1 minus sine squared theta, so 3 pi m 1 minus sine squared theta equals 4m sine theta. So 3 pi m minus 3 pi m sine squared theta minus 4m sine theta equals 0. So that's a quadratic equation in terms of sine squared theta. So 3 pi m sine squared theta plus 4m sine theta minus 3 pi m equals 0. So this is a quadratic equation. So sine theta is minus b, so minus 4m plus minus square root of 16m squared minus 4 multiplied by 3 pi m multiplied by 3 pi m divided by 6 pi m. And of course, minus doesn't suit us, it has to be plus. So sine theta is minus 4m plus square root of 16m squared plus 36 pi squared m squared divided by 6 pi m. And yeah, then you just thought theta is arc sine of that monster. Okay. Okay, slightly. I might have made a mistake somewhere, but I might have made a mistake somewhere. Maybe it's not that complicated, but you got the idea. So the main idea, like because everything starting from here, that's just maths. Maths starting from here. The physics, this is where physics ends. This is physics. Physics. This is the hard part. Like honestly, like because like solving equations, you can solve an equation. Okay, you can solve a difficult equation. You can ask a computer to solve a difficult equation. But the setup you have to do yourself. So you can see that when the mass tilts, the center of mass of the big mass moves to the left, and the small mass stays on the right. And then the center of mass will be always directly above the point of contact. And once you figured out x1, x2, m1, m2, that's done. That's the problem is solved. Right. I think there's another question here. If yes, mass is only area times density when the object is uniform. Yes. Of course. If the objects aren't symmetrical, we break them down into known objects, right? So, like if an object is of an irregular shape, we break it down into objects of known shapes, right? Yes. Okay, I have done this webinar. This is probably the seventh or eighth time I'm doing this webinar. So, you can have a look at the previous ones. I do have lots and lots of questions that I have prepared in the previous years. So if you are still confused. And yeah, so I'll see you in 2 weeks' time. The next time I see you is, let's see, 10, on the 10th of December for some differentiation and integration. So I'll see you in 2 weeks.